research and the director of doctoral studies years ago. He has a joint appointment at Yale's Environmental Engineering program. He has founded Yale Center for Coastal and Watershed Systems in 1992, and he acted as its faculty director for many years. He is currently also the faculty director of the Hixon Center for Urban Ecology here at FES. Gabe received his bachelor's degree from Yale, from the Department of Geology and Geophysics, where he studied environmental chemistry. And then after 3 years of working in an independent environmental consulting firm, he went on to get a master's degree in water resources engineering from MIT, and then following that, a PhD in environmental chemistry from the MIT Woods Hole Joint Program. Gabe is a nationally recognized expert on environmental chemistry and the impacts of land development on water. His research includes urban environmental issues and watershed-based studies of non-point source pollution. Among his many publications, he has co-authored the book called New Strategies for America's Watersheds, Integrating Ecological, Economic, and Social Factors, that was published by the National Academy Press in 1998. So the little tidbits that most people in this room probably don't know. In 2015, Gabe rode his bike from New Haven all the way to, guess where? West Coast, to Madison. He went all the way to the West Coast, to the Pacific Ocean at Florence, Oregon, a distance of 3,507 miles. Wow. Lived to tell the tale. He is also the holder of several age group records in local foot races. So please join me in welcoming Gabe.
Is this on? Yeah. Thank you, Karen. I am happy to be here and share my work with folks. I'm also pleased to see that there's a lot of staff people here. And I'm going to be talking about research that I've been doing looking at contaminant transport, especially metals, through estuaries. And kind of as a hook, and because I think a lot of people who aren't scientists aren't familiar with mass balance as a tool. It's a very powerful, simple tool, but it's something that I think can all relate to because it's very similar to what we do when we balance our checkbooks each month. So I want to start out by giving you a fair amount of context in three categories. One is talk a little bit about the urban water cycle, which is something which is very important to me. And then talk about this mass balance method. And then talk a little bit about some related previous research, because the project that's most active in my lab right now has its seed in work that I began 2 decades ago. And I'll explain why I'm still doing that today. And it actually gives it, I think, great currency and resonance that we've been looking at this for a long period of time. But then the bulk of the talk, I'm going to be discussing some current research that I'm doing on the West River and Mill River, which are 2 of the 3 rivers that flow through New Haven to Long Island Sound. Okay, so context, first part of that. Here's a view of New Haven from 12,000 feet, thanks to Google Earth. And I think what's clear here is that we have an urban area. There's a lot of hard surfaces. And the population density, I was just looking at this, is about 7,000 people per square mile. So it's not the very high end of that range, but it's certainly what we would consider to be an urban area. I thought it's really interesting that there's a hashtag in the city. And so hashtag estuary research, okay? That's some kind of building. But this is an urban area, and you can begin to see already that there is these rivers that flow through it. So we have this urban water cycle. And I think we tend to say, okay, city, the environment is dominated by people. And you can look at different components of the environment. The one that's most important to me is water. And when I started to do the calculations, I realized that people are not necessarily dominating the water cycle. So here's one way to think about this. If we take the area of the city of New Haven and think about all the precipitation that lands on it in a year, in these units, which don't really matter, is this big blue bar. If we then compare that to the part of the water that people use and alter in some way, and the best way to get at that is to look at the sewage treatment plant for the city of New Haven. Think about all the water that flows through it in a year. It's almost the entirety of all that rain, right? So you could argue, people are influencing 100% of the urban water cycle for this city. But you have to remember there's 3 rivers that flow through the city as well. The Mill River, the West River, and the Quinnipiac River, the Quinnipiac being the biggest of the 3. None of them are huge, but they're significant rivers. And when you start to compare that amount of water to the amount that people are using, it looks like we're not really dominating the hydrologic cycle. And if we think about tides, the water that's flowing in and out of New Haven Harbor every day, that's really the big story. And we aren't influencing that. We could have, there's tidal energy to electrical conversion. We don't do that. And we aren't really influencing the tides in a big way. So, are people dominating the hydrologic cycle in the city or not? And when I've shown this slide, sometimes people say, well, the tides, why do tides even matter? Well, I hope that by the end of the talk I'll convince you that they can matter quite a lot. Okay, so take home here, people influence the urban environment, but they don't necessarily dominate it in the way that we might think at first. Second part of the context, the mass balance method. And here's one of these, if you've ever seen Tom Gradle give a talk, these kinds of stocks and flows where we have pools of things and then fluxes between them. And this is from some work that I did looking at New Haven Harbor and thinking about all of the sources, sinks, fluxes for 4 metals. And I'll show you a little bit of the data later just quickly. But there's lots of pieces to this, right? But I think it's kind of an intuitive sense, right? We have different compartments where stuff can be resident for a period of time and also fluxes between them. Well, here's where we get to so here's a picture showing all of those pools, right? So New Haven Harbor, which is the central part of that study, but we see metals that comes in from industry, which turns out to be very small these days, from sewage treatment plants, STP, that's maybe a jargon thing that you may not be familiar with, and losses either to Long Island Sound, burial and sediments, but also we have this big watershed up here and the rivers that are flowing into the harbor, and they can be carrying substances like the metals. However, we have a marsh sitting there as well, and so that acts as a kind of a filter for metals that are coming down the river before they get to the harbor. And what we do, it's pretty straightforward, but sometimes the measurements can be quite extensive. For each of these pools, we go and do enough measurements that we capture what its magnitude is. And just as an example, let's think about, first, the tagline in the title of this talk is I think we're all familiar with this kind of a tool because we have personal finances, right? And so we have our checking and savings accounts, we have money that comes in from interest, that goes out to taxes, to mortgage payments, bills, and then we have long-term savings for, if we have kids, for college savings, for retirement, and so on and so forth. And you could add different boxes and fluxes there. But we're doing exactly the same thing. It's just that instead of the bank statement providing this information, we have to go out and do lots of measurements to figure out what the sizes of these pools are and what the size of the fluxes are. Okay, so let's go back to the New Haven metal mass balance and think about just one of the terms, this big marsh that sits just upstream from the harbor. And a lot of that material comes in, goes out into the wetland and gets buried. And so it's acting as a kind of a filter. It's providing an ecosystem service. Okay, so if you go along Route 91 up north, you see this landfill, but we see this big salt marsh complex over there as well. And what we did is we took samples from many different locations and measured the metals in the sediment, and from that observed, and then we did this little trick where we kind of straightened out the wetlands so we could see how far our samples were either upstream or downstream, and plotted them as distance. And I'm sorry, I'm going to be jumping back and forth from metric units to imperial ones, so I apologize for that. But what we saw is this simple pattern, and from that we were able to assign a value to how much lead and other metals was being captured in that wetland. This is a place where Chimianisfeld does a lot of work as well, looking at relative sea level rise and whether the system is keeping up with relative sea level rise or not. But it did require us to take 33 samples, which is not trivial. And from that, we're able to assign a value, and now we're looking at all those same pools and fluxes and thinking of their magnitude. So the beauty and the power of this is we can think about a bunch of sinks, a bunch of sources, and then their difference, which is going to be that term. And you might say, well, why is this sink a positive value? It's really because when you look at the other metals, it actually is a sink rather than a source, and I wanted them to be parallel to each other, so I apologize about that. But the big story here is it looks like, and this is something that we didn't know a priori, is that the big source for the harbor, at least for the metal lead, is the river. And these other ones, not so important. And so if you want to manage the system, you're probably not going to put a lot of your effort there. You're going to put it maybe into controlling the river if you want to control it. And then where does it all go? Well, it's not going out to, in this case, out to Long Island Sound. Most of it is getting buried in sediment in the harbor. And so then, in terms of management, if you do dredging, which you have to do periodically to keep the navigation going, you have to worry about that lead. Right? And that's something that we are dredging the harbor every 10 to 20 years, and disposing of those metal contaminated sediments becomes a problem. But the big deal, the bottom line here is, from the standpoint of management, you know what matters and what doesn't matter. Right? And you can also evaluate ecosystem services that are being provided by the system. So in this case, the ecosystem service is being provided by that wetland in removing a toxic metal. I like this historical information. Sometimes you can't find a lot of it, but here's an old study that was done in 1910 showing the city, and this is Frederick Law Olmsted Jr., and a vision that he had for the city. Boston has this emerald necklace of a series of parks around the city, and his firm also did a similar kind of analysis for New Haven and some other cities in the US. And the amazing thing is that almost all of these green areas, some of which the dark green I think were ones that existed at that time in 1910, and then other paler ones which were things that he was proposing, they've almost all come into existence. And I love this one because this brown area, brown field, right? You can't read this, but what it says is area destined to become freight yards. And then we had a couple of world wars, and some of that area did become freight yards, but actually today, almost the whole thing is the Quinnipiac River Marsh Wildlife Area. So he envisioned this kind of unhappy future where we had this just big industrial complex, but instead we have kind of a wonderful nature preserve instead. Okay, but I want to come back to this slide because I mentioned earlier that tides are a big part of the water budget in the city, and it's also the focus of the research that I'm doing right now. It turns out that tides are really difficult to measure, and these mass balances can be a very useful tool in two ways. One is, if there's something in your system that's hard to measure, you can get it by difference from a mass balance. And a good example of this I can think of is when I teach my course in the fall, we look at Hubbard Brook, and measuring deposition of sulfur, dry deposition of sulfur, is almost impossible to measure directly. And so what they do is they measure all of the other pieces of that system, and they get the sulfur deposition by difference. Well, that's one useful way that you can use a mass balance. But there's another way, which I kind of alluded to earlier, which is if you know every term in this, so we can get at tides if we can't measure them directly, and I'll show you in a minute that it can be very difficult to measure directly. But the other thing that you can do is if you do measure all of these pieces, remember that there was that difference term in my bar graph before. And you can do an internal check on the quality of your data, because if that difference bar is really small, and especially if it's smaller than the uncertainty that's associated with it, then we can say, aha, our data quality is good and our conclusions are good. So bottom line here is that the tides are difficult to measure, but they can be important. And so here's some data for the tides. In this study, we went out and sat in New Haven Harbor in a boat and measured, let's just look at the lead for now, and we measured both at the surface at 1 meter depth and also at the bottom of the harbor at 7 meters, and took these measurements, and what you see is there's no real pattern to that data, is there? And if we want to think about tide coming in, tide coming out, actually I think this is actually tide going out, tide coming in, and you integrate the amount of lead that left the harbor and came back in, you get a very small difference there, and so that's kind of problematic. When you get a small term that's a difference of two large numbers, you end up with a big uncertainty. And so when I think about that mass balance and those bars that we looked at earlier, there's a big range of uncertainty around that one term. And so it's good if we have all the other terms measured carefully so that we can get it by difference. This will illustrate the same point. Let me go through this quickly. We'll be coming back to this critter, Beryllium 7, later, but this is another mass balance that we did. Brantford River, just a few miles to the east. Similar kind of set of stocks and flows, and we did measurements, okay? And these things, the amount that is in sediments, the amount that's in the estuary, that's coming in from the watershed, the atmosphere, or being lost through radioactive decay, Beryllium 7 being radioactive, those are easy to measure. And in this case, we couldn't measure the tidal component, and so we got it by difference. So if we do a sum and difference of these other terms, we can figure out the amount that's going out to Long Island Sound. And in this case, it's a big number, right? It's comparable to any of these other terms, except maybe the big amount that's sitting in sediments. So that makes me uncomfortable in doing this kind of an analysis. I'd really, really like to be able to measure it directly. So fast forward to today, that's what I'm doing. I'll be talking the second part of this presentation about that. Ms. Bentley, please ask questions, okay? Okay. Third piece of context, and this goes back to the research that we started 2 decades ago, looking at the West River and what seemed to be a natural experiment that was about to take place. So this is a view of the West River with West Rock in the background and the salt marsh in the foreground. And some work that we did, a bunch of us, and I'll show you the table of contents for this study a little bit later. This was in the Yale Bulletin series, which I think is kind of unfortunate it doesn't exist anymore, because it's a great place to publish kind of gray literature stuff that we want people to get access to. But at about this location on this system, there are these tide gates. And there's also some over on the Mill River. And these are simply these flap valves that allow water to flow out on the outgoing tide, but close and don't allow water to come in. And I'll be talking a lot more about these things. I'll explain, why would you do something like that, too? Okay, so here's the table of contents. You can't read this, so I kind of blew it up. And what we did is, what was about to happen was that they were going to replace these valves with ones that were always open, except in the case when there was a big storm, and then they would close automatically to prevent flooding. But we saw this as an opportunity for a natural experiment, right? You go from a system which has been manipulated and shut down, essentially, to one that's open to the ocean. And we said, great, let's measure a bunch of things before that happens, and then measure those same things afterwards. So that was the impetus for this document that I just showed you, and here's the things that we studied. So things about people, things about the physical state of the system, soils, sediments, water, and so forth, and then a bunch of biological indicators as well. And the idea was, okay, what's it like today? And then what's it like after we open the system to flushing by salt water? And here's some example data. They had all of these sites, and they collected information about the plant communities and published that in there. And every one of those categories that we just saw, we had the same kind of pretty comprehensive evaluation. There's that hashtag again. We should go out there and do kind of a little art project or something. And this is the data that comes from it. So these are different, you can't read this, but these are different plant communities in the areas where they are important in this system. Our goal was to have a so-called before-after control impact type study where we have a control site that doesn't change and then an impact site that does, and then look at the before and after conditions. And so we've done that before, and we're expecting an imminent change to this flushing, and it turned out it didn't happen for 15 years, simply because they couldn't find funding to do it. But it has happened now. The system responds, when you think about all those different characteristics, the physical and biological and human ones, on different timescales. And it turns out, and I'll show you data, that the hydrologic chemical part of it happens instantaneously. But things like the plant communities and the animals that live there, and then the way that people value and use the system don't change for periods of time that are probably measurable in decades. But here are the control and impact sites. So there's the impact site, the West River, and there's the control site, the Mill River. Both of them, it turns out, this is amazing, they're adjacent, and they both have tide gates, even though tide gates are not that common. And they have almost exactly the same size watershed, very similar level of development, soils, climate, and so forth. So they're the perfect before-after control impact kind of study system. And there's, again, the control site, the Mill River, and thinking about the plant communities just like we saw for the west. Okay, so that brings us up to my current research. And this is a view in a painting by Frederick Church. This is up in the New Britain Museum of American Art, which is a great little museum. You should all go visit it. Showing from essentially the spot where the tide gate is installed today, and this is what we use for the cover of that book I just showed you, or that report, the West River flowing up past West Rock with sort of Westville off in the distance, and you see that there's some people here harvesting salt hay. And this gets to the part of the talk where I say, well, why would you put in those kind of weird flap valves and alter this ecosystem so completely? I mean, what happens is that fresh water builds up behind them as the tide rises, and then as the tide drops, the gates open up and the water flushes out, right? But salt water doesn't have a chance to get back in as the tide's coming in. Well, we actually don't know why these were installed in this particular location, but there's usually three different motivations. One is agriculture. It allows you to get equipment out on the salt marsh to harvest the hay. Mosquito control. And so this remains a problem. It turns out that these gates are not really good for mosquito control, but you're worried about West Nile virus and Eastern equine encephalitis and malaria, yellow fever, you name it, and you can be worried about mosquitoes as a vector. And then the third thing, of course, is flooding. And we're kind of lucky because, I don't know if this was intentional or not, both the West and the Mill River, in the portion that's kind of protected by the tide gates, we've never really built on the floodplain. And so protection is maybe not such a big deal in these particular systems. And you might look at this and say, well, this is something that you did with horse-drawn equipment back 100 years ago. Incidentally, Frederick Church never signed his paintings, but he always put a church in them so that his name appeared. A clever trick. I went on the internet, and you can still buy salt hay. You use it as mulch, and the good thing about it is it has no weeds, no terrestrial weed seeds in it, so you're not going to be putting stuff out there that causes weeds to grow in your backyard. Okay, let me talk a little bit about estuaries. People may not be familiar with these. It's just the name that we give to the zone where ocean water mixes with fresh water, right? So whenever you have a river, and there's some estuaries that arguably don't have a river associated with them, but usually it's a river, fresh water coming in at one end, and then tidal water that flushes in and out at the other, okay? So here's one cartoon, sort of a cross-section, and here's another kind of bird's eye view of the same thing. It turns out that from the standpoint of the hydrology of the system, these are the most complicated system you can come up with, because you have to worry about the freshwater river component, and you have to worry about the tidal flushing component as well. And superimposed, so we have the baseline flow coming in from the watershed. And then on top of all of that, you have storms that occur that can influence either the marine end member or the flooding that comes in from the watershed at the same time. So you got to do lots of measurements in order to capture all of the variability of the system. And here's a picture of the area that we're studying intensively right now. We're actually going to be expanding this to look at the Mill River in addition, but I didn't want to get into that part of it today. But here is the area that we're looking at, and just kind of to place you, here's our hashtag again. Here's Yale Bowl, okay? And New Haven Harbor would be sort of about right here. We're about a kilometer or less upstream from the harbor. This thing here, yeah, this is something that it's a reflecting pool that was, I think that was proposed by the Olmsted firm and was cut there. And they were planning to put a big obelisk here as a memorial for World War I dead, but that never happened. And Yale has used this as sort of a rowing course periodically, but it's sort of fallen into disuse. And it's a little complicated because you have this dead end in here, you have a big combined sewer overflow that comes into it, so the water quality and sediment quality up here is pretty bad. But water does flow in through the tide gates and then up through the natural channel here, eventually getting up to its tidal as high as Whaley Avenue, and then you have the whole watershed that's above that. But yeah, that's clearly not a natural feature. And systems like this one, it wouldn't be interesting to study if there weren't a lot of other ones. But if you go along the eastern seaboard, and in this case we're looking at Connecticut, the whole coastline is dotted with these things, right? And here's the two that we're studying, but here's the Branford River that I studied previously, and a bunch of these things. I hope that this purple color makes it stand out for you. Some of these have tide gates, but most of them do not. But a lot of them have characteristics, physically that are similar to the one that we're looking at, right? The other thing, when you think about it, if you look at these names, there's a lot of very expensive real estate that's adjacent to these. And so flooding and what happens when you have tide gates or not can be very important when we start to think about sea level rise that's going to be happening over the next century or two, right? So for all those reasons, good things to be studying. And these are just some topographic maps. Now, I showed you earlier on that slide a typical estuary, and they do tend to kind of widen as you go seaward. And here's one example of that, Coscob Harbor. So you can imagine that it might be easy to measure stuff at a point up here, the water that's coming in from the watershed, but it gets harder when you have this big diffuse cross-section. But either luckily or not, almost all of these have the Amtrak rail line or highways or things which act as pinch points where they're narrower and it might be easier to measure. And that's one reason that I like these tide gates, is it's a really convenient place to pull the whole system together and get relatively few measurements to understand the hydrology of these systems. And as I alluded to before, the US population, and I'm sure that Karen would say this is true globally, tends to be concentrated along coasts. Of course, in the US, we think of the Great Lakes as having coasts, so that might be cheating a little bit. But generally speaking, fewer people in the interior and a lot along the coast. And so estuaries is where the action is at, right? So these are important systems. Now, the other piece of this is what I call sediment dynamics. And I always like the way that Tom Sikkema would not talk about sediment or soil, he talked about mud, and made it very, I think, pedestrian, and that's what I'm talking about. When I talk about sediment, I'm just talking about dirt, basically, right? And dirt is important, okay? One is that the quality of the dirt and the rate that it accumulates is very important in terms of habitat, whether you have a rocky soil or a rocky bottom or a soft bottom. As I said before, navigation, this stuff builds up and you have to get rid of it eventually. Recreation, contaminant disposal, these are all big, expensive issues. And then from the standpoint of the chemists, people like me, we worry about contaminants, and particle reactive just means that things like metals and toxic organics tend to like to be stuck to dirt, and they don't like so much to be dissolved in solution. Graham, did you have a question?
Yeah, you showed that these rivers are huge sources of lead. Where does that lead come from?
Most of those metals are coming from legacy sources in a place like Connecticut. So you go upstream to a place like Meriden. Historically, they had metal fabrication. You know, Meriden is called the Silver City because of all of the flatware that was made there in the past, and all of those industries, it gets out into the environment, into the sediment and mud up there, and then over time it's gradually bleeding back out and coming downstream. All anthropogenic, and the numbers that I showed you are actually not, I mean, they're not super high. So it turns out it's not probably a big problem, but yeah, that's where it's coming from people as usual. So from the standpoint of the chemistry of the system and the pollution story, what happens with sediment is important. And so what we're doing is kind of threefold. One is we're looking at the water balance, the water mass balance. We're looking at the sediment solid mass balance. And then we're looking at stuff that's carried by the sediments, okay? So it's kind of threefold. And then the research questions that we're asking, these are some of them, is for the water, the solids, and the contaminants, where are they coming from? Are they mainly coming down from the terrestrial side, or are they coming in from the harbor? You know, the harbor's dirty too, and so is it a tidal problem, or is it a watershed problem? Is it both? And then if we can think of the estuary as being kind of a trap for these contaminants that are coming from land to sea ultimately, is it a tight trap or is it a leaky trap? And then ultimately we're worried about management, right? So what's the best management in dealing with contaminants or sediments or flooding? So the water, the solids, or the pollutants. Okay, so let's think about these tide gates, and this is the system as it used to be. They're very, I don't know, old-fashioned looking, aren't they? Sort of like Game of Thrones or something. You got these big wooden doors, and this is on rising tides, so they're shut. So the sea is out that way, right? We're looking from the downstream side. The tide comes in, they're closed. And then in some storms, water gets really high. I think this is Hurricane Sandy. They actually started to top the gates, and with a few more years of sea level rise, they'll probably be going right over the top of the whole system. They should probably be redesigned. And here are the same tide gates seen now from upstream, and in this case, there's some damage to this one gate, so water is leaking through. Okay, and then that was the conventional old tide gate. This is the so-called self-regulating tide gate, or SRTG. And they have this clever design, so they're kind of passive. They work passively. You don't have like a switch that you throw and make them open or close. When the water gets high enough, it raises these floats, and that causes the thing to hinge back down, and it closes them off, so water doesn't go upstream. And that's exactly what's happened here during storm surge. You can't really see it, but if you went underwater, you would see that these gates have closed down, and they're protecting the upstream side from flooding. And what happens is you have a lot of water coming through this. So this is just a little kind of impress on you that whole river and all of the tidal flow comes rushing through these things twice a day. Okay. Now, in doing the water balance, you can look at the upstream end of this thing, and it's pretty easy to figure out how much water there is because there's this very simple relationship between the height of water in the river and the amount of discharge, okay? People do that all the time. The tidal portion is a lot harder because there's not a simple relationship between how high the water is and how much flow is happening. If you think about it, the same level of water, the flow could actually be in completely opposite directions. So instead of having a simple system where you can just measure water depth and get a discharge, you actually have to measure flow directly. And we have these Doppler flow meters that allow us to do that. And then you can calibrate it by looking at by the tidal prism, which is the total amount of water that's come into the system or left it. Now that's great for one full tidal cycle, but if you're interested in what's happening on a much shorter time scale, and I'll show you that we care about that, you have to have direct measurements. So could anyone have told me who said time and tide wait for no man? It turns out to be Geoffrey Chaucer. Installing equipment in these things is pretty tricky because you got to catch it at low tide so you can get in there. And so here we are. I go in the water, Kevin doesn't, because I wouldn't make a student do anything that I wouldn't do. And the thing that's going to be happening is you'll see that the water starts to flow in pretty fast, and you want to get out of there at that point. Here's another one. This is one of those unself-regulated systems. It's currently broken and the door's off. Oops. And that's being fixed by the city, fortunately. And then this is one of the self-regulating ones. This is hard steel, and installing stuff in there is pretty hard, especially when you only have a few minutes before you're going to be drowned if you don't get out of there. And there's other methodological difficulties because this is what I noticed in that previous work is that this really sharp edge had worn through the cable, and it's not just like you can just replace the cable. You have to replace the whole device. And luckily, Yale has insurance, because we're putting very expensive, delicate instruments in a place where you saw earlier, there's a lot of stuff happening, okay? So it's pretty scary. Currently, there's nothing out there because the ice and so forth. And then biota are fighting against us. This is biofouling that occurs. Freshwater, you don't have such a problem. Marine systems, you get this crud, barnacles and everything else that wants to attack your systems. So methodologically, it's a pretty tough environment. And then on top of that, we have trees floating down from the watershed. And again, the city has been a great collaborator with us on this and getting crews out there to pull this stuff out. But let me tell you, these measurements are hard to do. Okay, so let's start to get to some of the measurements that we're doing. It turns out that you have to look at multiple time scales, some very short, and I would argue as short as a few minutes in some cases, up to much longer annual cycles. So over the month, we have big tides, we have small tides, depending on the position of the moon and the sun. And then, remembering back to our diagram showing the fluxes in the pools, some of it's accumulating in sediments, and we actually do lead 210 dating, and we're looking back in some cases to stuff which is many decades old. So we have to worry about timescales that range from a few minutes up to decades. That's actually the fun of it, I think. And here's a comparison of our control and our treatment site. So the west of the Mill River, before the self-regulating tide gates, they're very similar to each other, right? That's what we want. We want to control this just like our treatment. And then if this is during a period when there's no storms, when you have storms and these bars are rain events, they continue to match each other, sort of going up and down as the storm water comes in, and always that twice-a-day tidal cycle. But here's the really cool thing about these things. They install the self-regulating tide gates, and then they open them one day, and you get this big change. Okay, so now the treatment, the tidal range is twice what it is in the control. And here's the standard gates in blue, and there's the self-regulating gates in green. So the system changes from the standpoint of the hydrology very dramatically and very quickly. And we can document that and see how that influences the other parts of the ecosystem. And remember, this is what it's like before, and this is what it's like after. It's a big change, and if you go down and close these manually, which you can, it happens that day. It's not like something you have to wait for weeks or months to see the effect. So here's some data, some typical data. Looking at a short period of time, 2 days, and we've measured the water depth, which I think is something that is very intuitive. You have the tide come in, the tide go out, 4 tidal cycles over a 2-day period. And we have the flow, the blue line, and you'll see that, as I said before, the blue and the green don't follow each other exactly, and that's why you have to have a flow measurement as opposed to just a depth measurement. And then there's the turbidity, and turbidity is an easily measured surrogate for the suspended matter. It's the cloudiness of the water, and you can measure that in real time with a device, rather than having to take samples, filter them, and weigh them, and so forth. But look at the pattern, okay? The pattern is that you have big increases in the turbidity in the solids as the tide comes in, right? So it's here, tide's coming in, here, tide's coming in, here, tide's coming in. Okay, and I'll show you some other data from much earlier in a minute. And here's the flow, okay? Flow in, so the 0 on the scale for the flow is there. Big flow in, small flow out, right? Or sorry, big flow out, small flow in. And if we integrate those, we see that the flow in is much larger than the flow out. Why is that? Because flowing in, we only have those 3 self-regulating tide gates. On the outgoing tide, each is only 1/12 of the total. Okay, so we expect this is the behavior that we expect. And here's where we see if we measure turbidity, the cloudiness of the water, which is something we can do with a meter in real time as opposed to this very difficult measurement, we get this nice relationship, and so one of them is a good surrogate and allows us to figure out what the other one is doing. And anything that you can measure with a sensor like that, P, if we measured FDOM, for example, we could get a budget for dissolved organic matter using the stuff that we've got here now, so we should do that.
Okay. Is the turbidity just at the gate, or is the turbidity up and down the stream bed?
There's turbidity at many locations, but since we're measuring flow at that point, we want to measure turbidity at the same point. Right. And it's likely to be quite different if we went up and down the channel. Now here's some much older data from before the tide gate was installed. And look at the pattern here. It's quite the opposite, that the flow is coming out, and that's where we find these peaks in turbidity. And the question I am asking myself now is that because of the existence of the self-regulating tide gates? Is it just a difference in season? Because this is in April. The other data I just showed you was from November. Well, these are all things that we're going to be asking ourselves. And this matters because, if the sediment is coming in from the harbor, a bunch of things happen, including how you're going to manage the system. And if it's coming in from the watershed, you've got a different system. And so management would be completely different. And the other thing I want to point out is, we saw this data, okay, just a 2-day period. If you really want to understand the system, you have to measure it over long periods of time. And so this is a month's worth of data, and we're going to be collecting a year or 2 years worth of data. You end up with a lot of numbers. And so I like the idea that the school's going to big data analysis, because maybe whoever we hire in that area could help me out in handling these big data sets that we end up with. Okay, now the other thing that I really like about this system is you can do an experiment, okay? So here is the current system, the 3 self-regulating tide gates, and they stay open almost all the time. However, there are these doors that you can get up here and do a crank and lower them and shut this system down. So you can make it go from the current open system to what it used to be, a closed system, as an experiment. And the nice thing about that, so here they are closed. They closed them manually during Sandy. They were, I think, nervous that those balls weren't going to float and do the right thing, so they actually shut them down. But you can see here's the gate down in a position where it's blocking these things, right? And I can go out, and I don't see the city engineer here, but he said I have permission. I can go out there and close these things if I want to and conduct an experiment. And they've closed it, and you go back to the old domain. You close it one day, you open another. It happens instantaneously. It's really cool, I think. And we can manipulate a system which is about the size of the Yale campus and cause relative sea level rise to change by what's going to happen over the course of a century, and see then what it does to the chemistry and the hydrology, but maybe to other components of that system. Right? And so we're going to be doing that. Getting towards the close, these tide gates were kind of losing currency because people weren't worried so much about salt hay agriculture or mosquito control. They weren't working. But people are worried about flooding, and so they have these big, elaborate things. You probably read about this in the popular press. For example, in the Venice Lagoon, where they have these tide gates that close to protect Venice from flooding almost on a daily basis. And here's another local example that you may be familiar with. After the 38 hurricane, there was a lot of flooding in the city of Providence, and they built these gates, which they closed manually. Big river, big harbor, a lot of money at stake because, indeed, they did build on the floodplain in Providence and lots of other places. And so the work that we're doing does have relevance to that. Now, I'm not measuring a system as large as this, but usually you start with the low-hanging fruit, the systems that are easier to study. One other thing, and I was wondering whether we had time to get to this or not, but I think we will. We're also in the system looking at a tracer, and I think you've probably all seen systems like this where you put some dye in water and then you follow what it does, how it behaves downstream, and sort of understand how the flow of the system is working. We use a natural tracer, this beryllium-7 that I showed you on an earlier slide, which is produced naturally in the atmosphere. It's radioactive, but it's produced naturally from cosmic rays hitting carbon and nitrogen in the atmosphere and generating this radioactive isotope, which has a half-life of 53 days. So it gets introduced as a pulse every time it rains. Some of the stuff washes in, and you have a lot of it. And it behaves like, remember I use the term particle reactive, so things like lead. It's like you throw some lead on your system, but in this case, it's a naturally occurring substance which will be there for a period of time, but eventually will decay away and get lost. And it provides information about how these contaminants, other contaminants that behave like it, things like lead and mercury and other things that we worry about, on a kind of a day-to-month time scale because of the half-life. And as I said, it's particle reactive, so it acts like these other contaminants. And it decays away in a period of a few months. And then this works best when you have a rainstorm, a long dry period when the stuff can decay away, and then another rainstorm. But it turns out that happens not infrequently. Okay, so some conclusions so far. Doing continuous flow measurements, and I hope that this would work, but it turns out it does work. You can do that in these systems working around these methodological difficulties of trying to get equipment in there during a short period of time when the tide is low, dealing with the high turbulence, the kind of the violence of the water at that location, and the debris that's coming down from upstream. We've made it work. It looks like you do have to make measurements that have time scales from a few minutes, and we were doing some of the measurements of turbidity on a 15-minute time scale, and we realized that we're still not capturing all the variability in that system, and we're moving backwards or downwards to a 5-minute sampling interval, even more data to worry about. But stuff is accumulating in sediments that collects over periods of decades, and so we have to worry about all time scales from minutes up to decades. And if you think about it, your personal finances, same thing. You're paying bills every day, but you also have retirement account that are worrying about things that are happening decades in the future. Mass balance is a very powerful tool for working with these systems, and as it says, sediment dynamics are complicated, and they will require us to look at this system for a period of a couple of years. Luckily, I have the promise of funding from NOAA, as long as they don't zero out the budget, which seems to be a concern at this moment. And thanks to a bunch of people, Kevin Doms has done a lot of this work, and including getting pots of money from around the university to help support it before the Sea Grant funding came in, and the City of New Haven Engineering Department has been a great cooperator as well. So, with that, I'll end. This shows an old map that illustrates what at the time were marsh areas around the city, around the region, and our two study sites, the West River and the Mill River. Any questions?
Yeah, Gabe, you started talking about contaminants. That was the focus, and most of all, it was heavy metals, specifically lead, and then you talked about turbidity, so you were referring to organic matter. Are you also measuring nutrients? Because nitrogen and phosphorus, if you're thinking about point sources like sewage plants and rivers, there would be lots of transportation of nitrogen and phosphorus, which in high amounts would also be contaminants, especially if you're thinking about health, human health, agriculture, eutrophication, everything.
Yeah, well, that's a great question. Obviously, we get the most bang for our buck when we have things that we can measure in an automated way, right? So that's where turbidity equals suspended matter equals mud is a good one. For the metals, we're actually going to have to go in and take grab samples because in real time you can't measure things like lead. It's way too low. However, there are systems that will measure some nitrogen compounds in an automated way. They're a little more expensive, but not a lot more than the kinds of things I'm using now. And so, yeah, I was thinking, once you do the water, everything else is a bonus. And so we want to piggyback on this as much as possible, other things that we can measure in an automated way. And so, actually, in my office today, I was thinking that exact thing, that we should be looking at nitrogen. Yeah.
Other questions? Gabe's teaching in 5 minutes.
I must have explained it either extremely well or extremely poorly.
These floodgates seem to be prime locations for turbine applications for alternative energy. Have you thought about the effects of placing turbines in these tide gates?
I haven't, and I'm not aware of any place in Connecticut where they're using tidal energy to produce electricity. But I mean, you can see these things when the tide gets really rip-roaring, there's a lot of energy there. And indeed, putting in turbines seems like a great idea. Okay, well, I'll go teach then. Thank you.